night, imagine the unimaginable. Everywhere, nature becomes the enemy of all humanity, and everything changes. It may have happened 1,500 years ago. What could have so violently changed our world? Uncover the secrets of the dead. Secrets of the Dead was made possible by the Corporation for Public Broadcasting and by contributions to your PBS station from viewers like you. Thank you. "1,500 years ago, something extreme happened to the world's climate. Something that must have terrified those who witnessed it. The sun began to go dark. Rain poured red, as if tinted by blood. Clouds of dust enveloped the earth. Cold gripped the land for 2 years. Then came drought, famine, plague, death. Whole cities were wiped out. Civilizations crumbled. There is evidence of a catastrophe whose consequences affected the entire world and may have changed the course of human history.
The mid-6th century catastrophe was the most important date in the history of the past 2,000 years. It really did lay the foundations of the world we live in today.
From the attic of his unassuming suburban home, David Keyes, a writer on history and archaeology, has developed a controversial theory about an ancient catastrophe. For 5 years, he has investigated, consulted with more than 40 scientists and scholars, astronomers, physicists, climatologists, and historians, experts on cosmic collisions, volcanoes, epidemics, and ancient wars. From Mexico to Byzantium, from Africa to Indonesia, he has scoured the annals and chronicles of the 6th and 7th centuries AD. The result is a book that tells the story of a catastrophic climatic event buried in the heart of the Dark Ages, an event Keyes believes totally altered the course of world history. The mystery that has consumed him first presented itself at a conference on archaeology in 1994.
One particular talk really amazed me. It was a lecture given by a dendrochronologist, an expert in tree rings, called Mike Bailey, and he was giving a lecture about how all the tree rings in the world really went haywire somewhere in the middle of the 6th century.
Mike Bailey is an archaeologist and paleoecologist at Queen's University in Belfast, Ireland. He has a special interest in volcano and comet-induced environmental change. and uses tree rings to track significant climatic variations. Annual tree ring growth was discovered by the ancient Greeks, and as far back as Leonardo da Vinci, the connection between climate and ring growth has been known. Trees have always had the potential to become silent witnesses to thousands of years of climatic change. Every year, trees put out a new layer of growth within the bark. These layers show up as rings. Each ring varies in width. A wide ring indicates favorable growing conditions. A narrow ring, harder times. The pattern of wide and narrow rings is distinctive. Mike Bailey and his colleagues developed a high-tech method to tap into this resource. By feeding specific tree measurements into a database, each ring sequence could be matched with rings of previously felled trees and precisely dated. A bigger climatic picture began to emerge.
Over the last 30 years in Northern Europe, a variety of people, a variety of laboratories have set out and worked back from known felling dates, taking you back through long ring records of living trees and then overlapping to patterns from historic buildings, for example, fitting together these sort of long ring patterns, going back hundreds and eventually thousands of years.
It is by painstakingly analyzing and overlapping the patterns of older and older trees that a complete unbroken record of tree ring width is built up.
So you've got this sample with its very clear character change just here. When we processed another sample from the same building, we could see that it came originally from the same parent tree, and you could extend the pattern back from the first sample right back through to the beginning of this sample.
Many samples have to be analyzed by a computer program to get the average width for every year. It took Mike Bailey 14 years to build up the complete data just for Irish oaks. This tree record is now telling scientists what the weather was like every single year for the last 7,500 years.
If you think about that, that's an astonishing position to be in. We can interrogate for any calendar year in the last thousands of years what trees thought of their growth conditions over a big geographical area. And that information simply didn't exist before. But what we're interested in is, why did this tree go narrow at this point and narrow again at this point? What is the environmental information which is actually stored in the patterns?
David Keyes wanted to see for himself the mysterious 6th century event stored in Mike Bailey's tree rings.
Yeah, shuffle through here, David.
It was 10 years ago that Bailey noticed his mid-6th century AD oak rings went abnormally narrow, a sign that something very powerful was slowing the tree's growth.
539, 540, 41, 42, extremely narrow.
And he has corroborating evidence from a colleague in Finland.
He sees a really abrupt drop in 536, a bit of a recovery in 537 and 38, and then it drops dramatically into 542. So you begin to see a pattern.
The pattern was not just confined to Ireland and Finland. David Keyes began contacting other labs and found that almost everywhere he looked in the mid-6th century, trees were showing unusual growth patterns indicative of cold conditions. Foxtail pine rings from the Sierra Nevada mountains in California showed that 535, 536, and 541 were 3 of the 4 worst years in the past 2 millennia. In Chile, Fitzroy trees record the greatest summer growth drop of the past 1,600 years, as do Scots pines in Sweden. In Siberia, a 20-year decline in tree growth that began in the 530s was the most serious in the past 1,900 years. So what happened to the trees? Was it darkness, cold, natural pollution, or drought? Mike Bailey looked for the answer in a microscopic examination of a 536 AD oak ring. He found evidence of drastically reduced summer growth.
Just for interest's sake, a colleague in Germany sent me this photograph of one of his German oaks. The tree puts on a line of these large spring vessels, and it then puts on fine-celled wood during the summer and goes dormant, and then it does again the next year. So each year's growth is from the beginning of one line of vessels to the beginning of the next. And in this year, the year 536, the vessels are enormously small, and they're also distributed right through the summer. So it's widely reckoned that this phenomenon is due to frost damage.
The evidence was adding up. The implication was of missed summers and long stretches of extreme cold in the mid-6th century. And Mike Bailey also had archaeological evidence from Ireland to back up this theory. Much of the wood that he has dated came from crannogs, wooden forts built over water where people sought refuge during times of trouble and clan warfare. Bailey took keys to the remains of one crannog in Loch Catherine, near Belfast, to look at the submerged timbers that once formed the outer wall.
My first inkling that there was something going on came from timbers, specifically from sites like this.
The mid-6th century marks the beginning of the construction of crannogs. Bailey sees a strong connection between the need for such forts and the deteriorating climate.
When you look at the overall picture, there seems to be about a decade of really bad conditions, starting in 536 and running on to the mid-540s at least. The implication from lots of bits of evidence is that it was extremely cold, and that this reduced sunlight and cold caused crop failures. So basically, people in an area like this would be forced back onto non-agricultural produce. They would be forced to fish, they would be forced to hunt, and that would put a lot of strain on a population which was used to having agricultural produce to see them through the winters, for example. So I think things would have been fairly bleak here.
Keyes was hooked, not just by the tree ring evidence that it was cold, but because people seemed to be suffering. His next step was to see whether there were any written historical accounts that described a climatic catastrophe during that period. The mid-6th century is the time of the Dark Ages in Britain, and little writing survives from that era. But by far, the greatest civilization of the time was the Roman Empire. Rome had been sacked 100 years earlier by Huns and Goths. Now it was resurgent. With a new capital in Constantinople, it was winning back territories throughout the Mediterranean. By contacting classical scholars, Keyes unearthed many highly significant Roman accounts of bizarre weather. One eyewitness, a Syrian bishop, John of Ephesus, describes the extraordinary events during the years 535 and 536 AD.
There was a sign from the sun, the like of which had never been seen or reported before. The sun became dark, and its darkness lasted for 18 months. Each day it shone for about 4 hours, and still this light was only a feeble shadow. Everyone declared that the sun would never recover its full light again.
One of the consultants David Keyes contacted, Mike Whitby of Warwick University, sees great significance in these records.
Historians of the 6th century empire do not usually record climatic events unless they are something really stupendous. A natural event like a comet will get mentioned. Now, in the 530s, the fact that John mentions a 2-year dimming of the sun indicates that it was significant. John, writing in Constantinople, mentions it. Cassiodorus, writing in Italy, he too refers to a dimming of the sun.
We have had a spring without mildness and a summer without heat. The months which should have been maturing the crops have been chilled by north winds. Rain is denied, and the reaper fears no frosts. These accounts from the Mediterranean and the Middle East were extraordinary on their own. But what about the other civilizations of that time? Keyes scoured records from North and South China, Korea, and Japan.
And as it turned out, there were, out of, say, well over 30 sources, there were around a dozen which actually refer directly to the darkened sun event or to its consequences, to its immediate climatic consequences.
In 540, the Japanese great king wrote, "Food is the basis of the empire. Yellow gold and 10,000 strings of cash cannot cure hunger. What avails 1,000 boxes of pearls to him who is starving of cold?" The Nanxi Ancient Chronicle of southern China records, "Yellow dust rained down like snow. It could be scooped up in handfuls."
As the research continued, I began to realize more and more that this disaster had really enveloped the entire world, that it just wasn't just a few places, but it was virtually everywhere.
Armed with historical evidence of a global disaster, Keyes turned back to science to look for a culprit. Climatologists had only one explanation for such sudden extreme global cooling and visible darkening. A dense veil of dust, ash, or acid thrown up into the atmosphere, blocking many of the sun's rays. Only 3 suspects could have caused such a phenomenon: a volcano, an asteroid, or a comet. David Keyes tried to imagine what life would have been like for the people who witnessed the catastrophe. Were they engulfed by permanent winter? How would they have explained why the sky was dark and their crops were failing? Would there have been clues to the cause of the disaster? At Los Alamos, the birthplace of the atomic bomb, scientists have been studying all the possible atmospheric consequences of nuclear strikes and cosmic collisions. Keyes turned here to examine the likelihood that the cause of the catastrophe came from the sky.
We certainly have plenty of evidence that the Earth is struck repeatedly by asteroids large and small, comets large and small. You have to have a big thing that hits the ground in order to have a climate effect.
Extraterrestrial bodies come in all shapes and sizes. Meteors are small rocks that roam space, occasionally hitting planets, usually causing little damage. Asteroids are big meteors. When these objects hit the Earth's surface, they explode, churning up vast amounts of dust and debris. David Keyes turned to an astrophysicist to calculate how big an impact would have been needed to generate a climatic catastrophe lasting at least a decade.
Or even thinner, then L is the length of that scattering haze. Yeah? And so what we can say is that the total number of particles in the atmosphere, because this is 1, then rho is around 1 over kappa L. To cause a major climatic catastrophe that would last decades, we would need an impact by a rather large asteroid, say 4 kilometers across.
It would take an even bigger comet to create the same effect. Comets consist mainly of gas and ice, which give them their distinctive tails as they move across the sky. Because they are less dense, Alan Fitzsimmons has calculated that it would take a 6-kilometer wide comet to affect our climate. His calculations are supported by the 1994 impact on Jupiter by comet Shoemaker-Levy.
We saw a lot of the models and a lot of the calculations we had made about an asteroid or comet strike on the Earth vindicated. We saw the huge plume of debris of both of Jupiter itself and the vaporized comet rise up in a huge mushroom cloud 2,000 kilometers high above the atmosphere of the planet. And then we saw it crash down again, covering an area the size of the Earth in a fine layer of dust, significantly cooling the atmosphere and the planet underneath.
Fitzsimmons describes how spectacular such a crash might be on Earth.
When it was just over 2 days from impact, it would only be seen as a very faint star in the night sky. Now, as it approached us, as it got closer and closer, we'd slowly see it brighten and grow larger until about 30 minutes before impact. It would be about the brightest thing in the sky, and by then, of course, we believe everybody would have noticed it, but we wouldn't be able to do anything about it. Now, the time it takes for that asteroid to travel from the top of the Earth's atmosphere until it reaches sea level is only 8 seconds. So we see this brilliant fireball, all the time, of course, making no sound because it's traveling about 20 times the speed of sound. The first sound we would hear would occur minutes after we see the huge flash of light when the asteroid strikes the Earth's surface and is instantly vaporized in a ginormous fireball.
Could this disaster have happened without anyone noticing it? No civilization of the time records any such event. In addition, scientists have found no evidence of a crater left by an impact from the 6th century.
I mean, that's just yesterday. In geologic time, it'd be a big crater. We'd know about it. Certainly that happened 65 million years ago when the dinosaurs died, but I don't think it happened in the 6th century.
And to cause such a global catastrophe, such a crater would be at least 10 kilometers large, possibly much larger, and there's no such evidence of any such crater on the surface of the Earth today.
But the lack of a crater alone does not rule out a comet or asteroid strike. 70% of the Earth is covered in water. Could the impact have taken place in the ocean?
If the asteroid landed in the ocean, then the initial wave caused by the impact would be miles high.
There would have been humongous tidal waves, big, huge tidal waves that would have swamped the coasts over the margins of whatever ocean it struck.
The waves would have traveled miles inland. Again, no civilization recorded such an event, and scientists have not detected any significant break in coastal plant life during that period. There did not appear to be any evidence that an asteroid or comet had struck the Earth at this time. But could there be another extraterrestrial explanation? Not a complete comet hitting the Earth, but one that had fragmented and scattered throughout the atmosphere. It's a theory tree ring specialist and former physicist Mike Bailey suggested to David Keyes.
Well, the bombardment event has been, if you like, classically defined as a large number of pieces of comet arriving in a short period of time and exploding in the atmosphere. And the model for that is the 1908 Tunguska impact over Siberia, which was a single object which probably caused about a 20 megaton equivalent size explosion.
The 1908 Tunguska event was an example of an airburst explosion. A lightweight meteor hit the Earth's atmosphere and exploded in the air. While the shock wave caused massive local destruction, there weren't enough microfine particles released to affect global conditions. But Mike Bailey claims that a whole shower of cometary debris hitting in a Tunguska-style event could affect the climate.
If you have a large number of those, you're going to just put a lot of material into the atmosphere, and you're going to cause a dust veil.
Bailey even turns to mythology to support his theory. He's analyzed the life and death of one of the most famous legends of all time and reached an intriguing conclusion. 6th century Britain was supposedly the time of King Arthur, king of the Celtic Britons. All the many legends tell that Arthur lived in the west of Britain, and that as he grew old, his kingdom was reduced to a wasteland as the British fought off invaders from Europe. Curiously, even though the Arthur stories were written hundreds of years later, many of them suggested that the date of Arthur's death was 539 or 542 AD, right in the middle of the climatic catastrophe. The legends tell of terrible blows that rained down from the heavens onto Arthur's people. Bailey believes that Arthur's death could therefore be a symbol of something that really did happen. Devastation by a comet as it shattered and crashed to the Earth.
Then you look at the mythology. You discover that Arthur isn't just somebody with a nice suit of shining armor and somebody sitting around a round table. And the origins of the stories are in Celtic mythology.
The myth that Bailey says Arthur is based on contain many references to sun gods with long arms rising in the western sky. He thinks this can only be a reference to a comet and its characteristic tail. For him, the evidence clearly points towards the sky as the source of the catastrophe. But David Keyes still wants to explore the possibility of a cataclysmic volcanic eruption. There is one hostile area of the Earth that could hold the crucial clue: the polar ice caps. For the past decade, multinational teams of scientists have been extracting 1,000-meter deep columns of ice from Greenland in the north and from the Antarctic in the south. While not as comprehensive as the information from tree rings, ice cores reveal yearly layers of fresh snow that provide a wealth of detail about what was in the atmosphere at that time.
The ice caps contains information on what happened in the atmosphere, like volcanic eruptions, asteroids coming in, how much dust was in the air. A lot of information. The chemistry of the old atmosphere is in there. And even the chemistry today is changing in our atmosphere. If we combine this, we can have a record which we can compare with other records from the deep sea sediments, from tree rings, from lakes. But the fantastic thing about the ice caps is that they are directly related to the atmosphere itself.
Professor Hammer's team is testing a new Greenland core from the 530s AD that has just arrived at their laboratory. If pieces of a comet or asteroid had exploded in the atmosphere, the team would expect to find traces of rare chemical elements like iridium. If there had been a massive volcanic eruption, however, they would expect an excess of sulfuric acid, the telltale signature of a volcano. The sulfates would have been hurled into the atmosphere and scattered by the winds. They would have returned to Earth in rain and snow, then finally been stored at the poles in ice.
And what we are going to do now is take a piece of ice out around 535 after Christ. We will have to clean it a little roughly here first. set up here, where it will be cleaned in the ends and on all sides, and then it will be cut by the steel knife, so that we are not touching the core. We have to remove quite a lot to be sure that we don't have any outside contamination.
The clean core is sliced into 5 centimeter lengths. Each length is then melted and analyzed.
They will be measured one at a time, automatically, from now on, and the results will show up on this computer as chromatograms.
What will the ice reveal? Cometary debris or volcanic sulfates?
Here I can see the sulfate peak is increasing when I go to the next sample. That must be come from sulfuric acid in the atmosphere, and that's an indication that there's been a volcanic eruption.
Apparently, it wasn't just any eruption.
And this, what is important, I'll show you here, is the sulfuric acid. And actually, these huge amount of sulfate here, lasting several years, and clearly higher than anything else in this part of the record, corresponds exactly to this around 535. So there's no doubt it's a major eruption.
The results from Greenland's N-grip core seem conclusive to Professor Hammer. Lots of sulfates and no cometary debris. But for the eruption to have had worldwide consequences, more evidence was needed.
If you want a climatic important major eruption, it must show up with a large signal in both hemispheres. That is, you must see it in Antarctic ice cores and you must see it in Greenland.
Current information from the Antarctic ice cores is incomplete, but Professor Hammer has found some evidence that indicates a volcanic signal in the southern hemisphere.
We have a volcanic signal which lasts several years. We have from an Antarctic core similar evidence as in Greenland, but not as good, not as well dated, but indicating that this volcanic eruption could have taken place.
There is evidence from both ends of the Earth of a sulfur spike around the mid-6th century. To Keyes, this strongly indicates the likelihood of a major volcanic eruption, just at the time he's investigating. And while the idea of a volcano wreaking climatic havoc may seem far-fetched, it is far more likely than a catastrophic cosmic collision.
Cosmic collisions are extremely, extremely rare. I mean, they only happen once every many, many, many millions of years, whereas volcanic eruptions are occurring, I won't say all the time, but they're certainly happening every few thousand years. You get a really major volcanic eruption.
And ice cores now show that every 1,000 years or so, massive climate downturns have occurred. The mid-6th century event is simply one of the most recent. In fact, what surprises volcanologists is how few volcanic eruptions there have been in the last 100 years.
One of the amazing things which people sometimes forget, even scientists, is that our century is one of the most quiet centuries with respect to volcanism.
Other eras have seen much more volcanic activity and much more ash in the skies.
If you go back in time, in 19th century and 17th century, 18th century, there's a lot of volcanoes. They come in lumps, say 20, 30 years, a lot of them. They even overlap in the stratosphere, mixing up.
Volcanic dust creates spectacular sunsets, which may have influenced the paintings of Joseph Turner in the 19th century.
And it's not speculation, but people do think that Turner's paintings with his sunsets, it was not the taste of the artist to make them so red as they were, but they were actually painted in a time when the real sunset looked like that.
live on this planet with over 200 active volcanoes. They may have been quiet recently, but a really massive eruption can turn the climate upside down. To create a dust veil that envelops the world, the eruption has to happen near the equator, as only equatorial winds can spread dust over both hemispheres. But there are over 90 equatorial volcanoes. Could David Keyes figure out which one caused the mayhem of the 6th century? Keyes began to narrow the search for the source of the 6th century eruption. He turned to ancient writings looking for mention of such an event. He focused on the area with the world's highest concentration of large tropical volcanoes. The volcanoes form an arc straddling Southeast Asia, and Keyes found what he was looking for in nearby China.
I, in great excitement, started looking to see whether there was any trace of anything happening in 535. And in fact, in February 535, there's a record of a loud bang, a huge thunderous sound coming from the southwest. And with this one, there was no mention of lightning or anything. It was merely the rather sort of mysterious entry in which they only referred to the sort of thunderous noise. And interestingly, that points straight towards that Indonesian area where all those volcanoes are.
The sound must have been extraordinary, if the Chinese bothered to record it. But could the sound of a volcanic eruption have traveled 3,000 miles from Indonesia to China? To answer that question, Keyes turned back to experts at Los Alamos Laboratory to explain the physics of long-range sound travel.
We know that near the volcano, the sudden explosive eruption provides a shock wave in the near field, and that propagates out, going out to thousands of miles. But as it propagates out, you lose the high frequencies, the shock, very sudden, sharp reports of the volcanoes, and all you're left with are the low frequencies that we measure in what we call infrasound, which is generally below 10 cycles per second. The long-range perception of that sound would be very low rumbling, much like very distant thunder. We're still talking about hearing it, so you're down at the very low end of the human response, and so it's going to be very low bass sounds, rumbling, thunder.
The Los Alamos experts had said it was possible. Now, could Keyes find any written evidence from Indonesia? Unfortunately, very little writing survives from the area. But once again, Keyes found a fascinating clue. Housed in the Royal Palace at Solo in central Java is a massive set of 95 manuscript volumes called the Book of Kings. It records all of Java's history and was put together in 1869 by a royal courtier called Rangwasita. Some is folklore and myth, but scholars believe much is based on genuine oral and written history, handed down through the generations.
Rangwasita was known to have done extensive field work, as it were, traveling all over the island of Java and into Bali, where it is said that he picked up, great caches of palm leaf manuscripts.
In one volume, Rangwasita describes an extraordinary event that took place around the middle of the first millennium. Javanese royal archivist Prince Puja reads from the original text.
A mighty thunder, which was answered by a furious shaking of the earth, pitch darkness, thunder and lightning, and then came forth a furious gale, together with a hard rain, a deadly storm darkening the entire world. In no time, there came a great flood. When the water subsided, it could be seen that the island of Java had been split in two, thus creating the island of Sumatra.
Had Keyes struck gold with the Book of Kings? Geophysicists he consulted said the story accurately described a major volcanic eruption that would have been difficult to invent. And the only major volcano in the specific area between the islands of Sumatra and Java, indicated by Rangwasita, is the legendary Krakatoa, the world's most notorious volcano. But could Keyes prove that Krakatoa was the culprit? Icelandic volcanologist Professor Haraldur Sigurðsson now joined the chase. He had studied the volcano and knew that Krakatoa's history hid details of an ancient eruption far bigger than any recorded in modern times.
About 5 years ago, when we were doing research on the 1883 volcanic eruption of Krakatoa, we discovered this deposit of a major eruption, and so we became very interested in this deposit, but at the time we didn't have the time and resources to study it in detail. So what we really want to do is ideally find charcoal within this layer or charcoal immediately above and immediately below it in order to give us a date of the event.
To give Professor Sigurðsson the opportunity to unlock the history of Krakatoa and search for the telltale charcoal, the film's producers decided to sponsor an expedition to Java. The goal? To test Keyes' theory by dating Krakatoa's major eruption. Krakatoa is part of a group of uninhabited rainforest islands lying west of Java and just south of the equator. In addition to the ancient eruption Sigurðsson is attempting to date, Krakatoa is also the scene of the most deadly volcanic eruption in recent times.
Well, Krakatoa became a notorious volcano in 1883 when the eruption killed 36,000 people, mostly by tidal waves, but also by hot ash clouds sweeping over the ocean and reaching the land and incinerating people on the shores around the Sunda Straits. It is a very difficult area for access, it's remote, and the conditions are harsh here. The environment is difficult.
The lava fields on the island of Anak Krakatoa will be the first stop for Sigurðsson and his team. Anak means child, and this child was born out of the 1883 eruption. In just over a century, it has grown into a 1,000-foot-high volcano. The lava, rock, and ash it frequently spews continues to accumulate. Anak is unpredictable, and each year it becomes bigger and more dangerous.
Now the volcano erupted this morning, a small Volcanian explosion as we call it. It threw out a lot of rocks and ash and created a plume rising up into the atmosphere. Now actually when you get up to them, these rocks are the size of houses and 5-6 meters in diameter. And these were ejected by the explosions of Anak, and they travel through the air like a bomb, basically, and they fall to the ground, and when they hit the ground, they create a crater. Well, this is about as big as they come. This one must be 2 meters high, and what do you think, about 4 meters wide?
Yeah, I'd say so.
That's a big bomb.
Yeah, beautiful crust.
Hard to imagine this thing flying through the air and landing here during an explosion. plunking down and creating this crater that it sits in. This one is a good one because you can hide behind it in an explosion and take shelter. Let's hope they don't land like this today. It'll be very dangerous.
Anak Krakatoa is a noisy and quarrelsome child. Only 2 hours after the team left the island, Anak let rip. Hurling rocks and lava onto the area where the scientists had just stood. From the safety of the sea, they gazed back on one of Mother Nature's most impressive fireworks displays. These pyrotechnics are part of a cycle that has been going on for hundreds of thousands of years. Krakatoa erupts, islands grow, till eventually they blow themselves apart. Sigerson's task is to journey back into history to try to discover when Krakatoa's major eruptions have occurred. For decades, scientists have thought that Krakatoa contains a centuries-old secret. Illustrations taken from a 1920s book show a possible pattern. First, there was ancient Krakatoa, which exploded, possibly around 535, leaving islands behind that through a series of minor eruptions grew into the Krakatoa of 1883. This, in turn, blew up, leading to the Krakatoa Islands of today. Sigerson's last survey of the island seemed to confirm this idea. 5 years ago, he charted the ocean floor using sonar. The charts show outlines of a caldera, the giant crater left after a massive volcanic explosion.
There's a structure out here in the ocean, a circular structure, which is much larger in diameter, and it is possible that this buried circular feature that we see here to the north and the east may in fact be a gigantic ancient caldera of Krakatoa. Well, we must be right on the edge here.
Can Sigurdsson find the hard evidence to date the major eruption of ancient Krakatoa?
It's a big cliff. Oh, yeah.
He is looking for charcoal, which is formed when hot lava instantly carbonizes trees. For precise carbon dating, Sigurdsson must find charcoal from the major eruption layer. Failing that, he can narrow the margin by finding charcoal in the layers above and below.
Wow, it's a vertical drop.
Still no easy task.
Yeah, it looks like okay all the way. I'm right in the middle of the this major pyroclastic deposit that is formed by a very large eruption of Krakatoa. Now this is very likely to be the deposit that was created by a eruption possibly in the 6th century AD, and this is the one I'd really like to get some charcoal from so we can date this very important event. Now we'd be very lucky to find charcoal, but I'm going to keep digging around here a little bit and see what we got.
The material in the volcanic debris layers left by Krakatoa spans hundreds of thousands of years. And there is very little charcoal to be found. So each precious sample has the potential to narrow down the date of the major eruption.
Often it's extremely difficult to find the charcoal. You might think that there would be a lot of burned wood or carbonized trees here because it's a tropical environment. But many volcanoes are barren because there's so much activity that the vegetation and the forest doesn't really get established. We've had a lot of problem with finding charcoal in this particular deposit, but we must keep in mind that there are only small pieces of the island sticking up above sea level, so we have a very small area to prospect.
During the 2 weeks he was in Krakatoa, Professor Sigurdsson was only able to find 10 charcoal samples. He found none big enough to carbon date from the major eruption layer. However, he did collect good samples from the layer immediately above it and from a layer a few levels below. The samples will now be dated to see whether the major eruption could have occurred in 535. If not, it is highly unlikely Krakatoa is the culprit, and David Keyes will have to rethink his theory. Weeks later, the carbon dating is complete. Professor Sigurdsson faxes the results and his analysis to David Keyes.
Yeah. So what's his assessment of it?
That's really good news.
The data shows that the layer immediately above the major eruption dates from 1215 AD. Carbon from several layers below is from 6600 BC. Back in his office, Sigurdsson was able to make a deduction.
Well, if we look at this in detail over here, then we have this picture. We have 1215 AD right on top here in this deposit. Then we have the major eruption deposit right underneath it. And then we have about 5 layers. And then down here we have the charcoal, and we dated at 6600 BC. So in here we have quite a period of activity and development of the volcano, possibly several thousand years. And that leads us to think that the event is much closer to 1215 AD as opposed to 6600. That span still covers the 535 AD event, so it doesn't rule it out at all. In fact, I think as a result of this, we are focusing more and more in on that time frame.
He thinks that the lead period, the lead option, if you like, for when the major eruption that we're talking about took place was the first millennium AD. So although technically it can be anything between 6600 BC and 1300 AD, all the other pieces of evidence that he's got suggest that it's actually, we can narrow that down to the period, let's say, 0 to 1000. Now, 535 is marvellously right in the middle of that window. So I think that it's looking good.
David Keyes' years of detective work suggest to him that there is overwhelming evidence of a massive volcanic eruption around 535 AD. While some scientists believe there is not enough evidence to point a finger at Krakatoa, others feel Keyes' hypothesis is not unreasonable. If Krakatoa was the cause of the climatic catastrophe, it had to have been a spectacular explosion. Such a cataclysmic eruption would have spewed ash and sulfur dioxide high into the atmosphere, enshrouding the Earth in twilight, causing global chaos, and changing the course of human history.
The sun went dark. The rains were heavy and crimson. The earth was covered in dust. Winter seemed eternal, and that was only the beginning. Uncover the disastrous effects that shook our world, as Secrets of the Dead continues in a moment. Catastrophe. Secrets of the Dead was made possible by the Corporation for Public Broadcasting and by contributions to your PBS station from viewers like you. Thank you. Secrets of the Dead is available as a 4-volume home video set for $59.98. Individual episodes are available for $19.98. To order, call 1-800-336-1917 or write to the address on your screen.
You're watching PBS.
This November, it's all about choice.
School in America for choice.
People seem to think that vouchers are some kind of Viagra for public school reform. It's really snake oil.
Who you choose could determine your right to choose where your child goes to school.
These kids need their education. They're not going to get it in a public school.
Challenge turn around. Choice accountability.
Frontline investigates the battle over school choice.
Tuesday night at 9 on the channel that changes you. When it's time to renew your membership to Houston Public Television, we have a history of not calling you, but you will get a calling for history. Call 713-749-8383 to renew your membership to Houston's History TV channel. Houston Public Television, the channel that changes you. On the next Battlefield 2.
The battle for the Rhine saw some of the most audacious and dramatic gambles of the whole war.
The Rhine River, a major obstacle to the Allied conquest of Nazi Germany and the liberation of occupied countries.
What no one had expected was that it would turn into a major battle, and one of the bloodiest yet fought by American troops.
The battle for the Rhine, next time on Battlefield 2.
The battle rages on, Thursday night at 7. From the campus of the University of Houston, this is Channel 8, KUHT Houston, a service of the University of Houston and supported through the Association for Community Television.